This video is on convergent sequences. So here's our definition. Let xd be a metric space, and let xn from n equals 1 to infinity be a sequence of points in the set x. Then this sequence converges to the point x in x if for any epsilon greater than 0, there is a positive integer n such that n greater than n implies that the distance between xn and x is less than epsilon. In this case, we say that x is the limit of that sequence and that the sequence is a convergent sequence and it converges to x. We sometimes write as notation that xn converges with a line to x. So what this definition is saying is, okay, we've got this sequence of points, x1, x2, x3. We don't really care what it's doing in the beginning, but what we're saying is that eventually it needs to get close to x. How close? As close as we want. So what we want to say is that for any epsilon greater than 0, there is some n in the natural numbers such that n greater than that n implies that the distance between those 2 points, xn and x, is less than epsilon. So we can choose any epsilon greater than 0, and there must be every xn such that n is greater than that n. So xn plus 1, xn plus 2, xn plus 3, all of those things must be in that ball. So they might be getting closer or not, but they must be inside that ball of radius epsilon. And then I could say, okay, well, that's nice. Now I want to give you a different one. Let's say, let's take my last epsilon and make it epsilon over 2. And then there's got to be some other n2 such that n greater than n2 implies the same thing, that the distance between xn and x is less than this new epsilon over 2. So I can make my epsilon whatever I want. I can make it as arbitrarily small as I want, and it must be the case that all infinitely many of the points of the sequence from then on is contained inside that ball of radius epsilon over 2, or whatever size I want. So to think about this a little bit more, here are a couple examples. So first we've got the sequence 1 over n from n equals 1 to infinity. And does that sequence converge to 0? In 1, does it converge in the usual metric on R? And 2, does it converge in the discrete metric on R? Next, let's look at the sequence an, where an is defined to be 200 for n less than or equal to 40, negative 200 for 40 less than n less than 1,000, and 5 for n greater than or equal to 1,000. Does that converge in the usual metric on R? And does that converge on the discrete metric on R? So please pause the video at this point, grab some paper if you don't have it already, and think about whether or not these sequences converge in these metric spaces. Okay, so does this sequence 1 over n converge to R in the usual metric? Yes, it does. So if we, let's say, let epsilon be greater than 0, we're not saying what epsilon is, it's just some presumably small positive number, but it is positive. Then that means that there is some n in the natural numbers such that 1 over n is less than that small positive number. This is something that we're assuming to be true, an axiom about the natural numbers. And therefore, it's the case that the distance in R is the absolute value of 1 over n minus 0, the distance between points in this sequence and the value that we're showing it converges to, is less than epsilon for n greater than n. Because if 1 over n is less than epsilon, we know that 1 over n is less than 1 over n for little n greater than big N. Again, this is something we can assume without proof. This is something that we know. If we make the denominator larger, the entire quantity is smaller. So basically, that's all we need. We have proved it. So yes, it is true, because for any epsilon I pick, eventually the distance between points in the sequence and the limit of the sequence is less than epsilon. What about in the discrete metric? Well, just as a reminder, our discrete metric, you should be used to it by now, but all distances are either 1 or 0. 1 if x is not equal to y, and 0 if x equals y. So let's let epsilon equal 1/2. It must be true for any epsilon. If we can show that this is false for any epsilon, therefore, then the sequence does not converge. So then there is no n in the natural numbers, such that n greater than n implies that the distance between 1 over n and 0 is less than 1/2. Why? We know that this is because the distance between 1 over n and 0 is equal to 1 for all n in the natural numbers. And because of that, that means that this sequence does not converge to 0 in the discrete metric. So it does not converge to 0 in the discrete metric. Okay, let's look at this other example. So we had this sort of strange sequence. AN is 200, 200, 200 up until 40, and then negative 200 for quite a while, and then settles on 5 for a while. So does this sequence, or for the rest of eternity, so does the sequence converge? We were asked, does it converge in the usual metric? Does it converge in the discrete metric? In fact, this sequence converges in any metric. Why? Because, so this sequence converges in any metric, and that's because the way that a metric is defined, so in the definition of a metric, if D is a metric, then the distance between x and itself must be equal to 0 for any point x. And so therefore, so this is just the definition of a metric on a space. So if it's a metric on a space, that must be the case. And so that means that the distance between AN and 5 is going to be equal to 0 for all n greater than or equal to 1,000. And whatever epsilon we pick, let epsilon be greater than 0, then the distance between AN and 5 is going to be less than epsilon for all n greater than or equal to 1,000. And so this tells us that yes, therefore, this sequence A sub n converges to 5 in any metric on the set that includes those values. Here's a theorem about convergent sequences in a metric space. So here's our theorem. A sequence cannot converge to more than one limit. I'm not going to do the full proof here, but I'll just do a quick sketch. So if we suppose for contradiction that some sequence xn converges to A and it also converges to B, where A is not equal to B, then what could we do? Again, by definition of a metric, we know that since A and B are not equal, that means that the distance between A and B must be greater than 0. So if we then let epsilon be the distance between A and B divided by 2, then we're going to end up with a contradiction, right? Because, here's A, here's B. It cannot be the case that there is some natural number n such that all points are both in the ball centered at A of radius distance between A and B over 2 and in this ball over here that's disjoint. So that is where our contradiction comes in, that it must be the case that there is some n in the natural numbers such that n greater than that value implies that it's both in this ball and in this ball, and that is not possible. So that is where the contradiction comes from. So this is just a sketch of the proof. but the full proof is in the book. I encourage you to think about writing up the details of this proof and then seeing how they did it in the book and comparing. All right, so here is, so that's just a sketch, but this is still a useful and important theorem. Next, let XD be a metric space and A subset of X. So same setup, and now we're going to talk about this next theorem about metric spaces. First, a point X in X is a limit point of A if and only if there's a sequence of distinct points of A that converges to X. So in other words, we're connecting this idea of limit point to convergence. So X is a limit point of A if and only if some sequence of distinct points of A converges to X. Secondly, a set A is closed if and only if each convergent sequence of points of A converges to a point in A, like not in some other place in the space X. So this is a kind of neat theorem because it's connecting all these different things we've talked about, limit point to convergent sequence. In other words, the limit of a sequence is the same thing as a limit point. And B, the set is closed if and only if any convergent sequence of points of A, if it converges, it must converge to a point of A, not somewhere else in the space. So let's now think about the proof of these pieces. All right, now let's start by proving A, and let's prove it in the forward direction first. Suppose that X is a limit point of A, and we want to show that there is some sequence of distinct points of A that converges to X. So we've got X, it's a limit point of A. What does that mean? One equivalent definition of being a limit point is that then for any epsilon greater than 0, there is an A in the set A such that A is not equal to X and A is in the ball centered at X of radius epsilon. So in other words, for any epsilon greater than 0, so there's our epsilon, there must be some point A other than the point X itself such that A is an element of A and A is in that ball centered at X of radius epsilon. In other words, the distance between A and X is less than epsilon. So this was one equivalent definition. Our original definition of limit point was that for any, limit point was that for any open set containing X, there is some point other than X itself that is contained in that open set as well as in A. But we know, sort of by properties of open sets, that also means there's some ball centered at that point X of radius epsilon with the same property. Okay, so what we're going to do is basically have a sequence of smaller and smaller balls centered at X that must each contain points of A that are of certain distance from X. So basically what we're going to say is first consider the ball centered at X of radius 1. By definition of limit point, this contains some point, and we're going to call it A1, which is in A and in the ball centered at X with radius 1, such that this A1 is not equal to X. So maybe I'll start with a new X over here, or I'll start with a new X over here just outside of A. All right, so we're starting with a relatively large ball of radius 1, and we're saying, okay, there's got to be some A1 that's in there, that's in the ball and in A. Now we want to make a new ball, and we're going to make it, this new ball we're going to let epsilon 2 be the minimum of the distance between this A1 and this X, and 1/2. So we're going to say, okay, making this new epsilon over 2, here's the distance between x and a1, and it looks like in this case, the way I've drawn my picture, 1/2 would be less than that because our original ball was of radius 1. And whatever the minimum of those two values is, the distance between a1 and x and 1/2, that is our new epsilon 2. And now again, by definition of limit point, the ball centered at x of radius epsilon 2 contains some point a2 such that a2 is not equal to x, and a2 is in this ball centered at x of radius epsilon 2, and it's also in A. So that's a2. And this is how we're constructing our sequence. Let's just do one more step of this. Now let's let epsilon 3 be the minimum of the distance between a2 and x and 1/3. So we're going to draw our a2. It's got to be somewhere in a2. And if this is the minimum between the distance between a2 and x and 1/3, then it looks like the distance between x and a2 would be smaller in this case. So that's going to be our epsilon 3, that distance. And then again, by definition of limit point, because x is a limit point, that means that the ball centered at x of radius epsilon sub 3 contains some a3 not equal to x, such that a3 is in the ball centered at x of radius epsilon 3, and it's also in A. So this is my way of constructing the sequence of points, a1, a2, a3, just continuing forward in the most general sense. When we we're going to let epsilon sub n be the minimum of the distance between a sub n minus 1, the previous point, and x, and 1/n. So that would be epsilon sub n. And again, by definition of limit point, there exists an an not equal to x such that an is in the ball centered at x of radius epsilon sub n, and it's in A. So now my claim is that an is a sequence and it converges to x. So claim a sub n is a sequence of distinct points that converges to x. So both those parts are important. So the distinct part is guaranteed by this definition of being the minimum distance. This epsilon n is going to be the minimum of the distance from the former point to x and 1/n, whatever that is. So that's what's going to help me with the distinct part. So since epsilon n is less than or equal to the distance between a sub n, or a sub n minus 1, and x for all n, that means that an cannot equal a sub n minus 1, since a sub n minus 1, the distance between a sub n minus 1 and x is equal to epsilon, which implies that a sub n is not an element of the ball centered at x of radius epsilon. That's the set of all things such that the distance between x and an is less than that value. Because of this, that means that the an are distinct, or in other words, not equal to one another. So the points are distinct, and to show that it converges to x, that is guaranteed by the other piece of this minimum. So being also less than or equal to 1/n, this tells us that since epsilon n is less than or equal to 1 over n for all n, this tells us for any epsilon greater than 0, there is some n such that 1 over that n is less than epsilon. And so that means that for n greater than n, the distance between x and an is going to be less than epsilon sub n, which is less than 1 over n, which is less than epsilon. Great. So this is a sequence of distinct points, and it converges to x. So a sub n converges to x, and that is what we needed to prove, that those points were distinct and that they converge to the point x. Let's now prove the reverse implication for this theorem. So let's suppose that the sequence x sub n is a sequence of distinct points of A converging to X. So, okay, we want to show that X is a limit point of A. So that's what we want to show. Let's then let epsilon be greater than 0. We want to show that any ball centered at x of radius epsilon contains a point other than x that is an element of A. That's what we want to show. By this definition of being a sequence of convergent points, that means there exists some n in the natural numbers such that n greater than n implies that the distance between x and x sub n is less than epsilon for all of those n. Now these are distinct points, and the only really important part of that here is that they cannot all be equal to x. At most, one of these points is equal to x. So at most, 1 x sub k is equal to x, because these are distinct points. Maybe one of them happens to be equal to x, but at most one of them can be. Since the distance between x and x sub n is less than epsilon for all n greater than n, then for xn not equal to this particular xk, that means that xn is not equal to x, and xn is in the ball centered at x of radius epsilon and also in the set A. Therefore, that means that x is a limit point of A. We have met the definition of being a limit point of A for any epsilon greater than 0. The ball centered at x of radius epsilon contains some point of A other than x itself. So we have proved A of this theorem. Now let's look at part B of this theorem. A set A is closed if and only if every convergent sequence of points of A converges to a point in A. This is something I would like you to know. I would like you to read over this proof in our book. If you want, I would encourage you to just think about, the definitions that we have before, the theorems that we have before, and maybe just do a quick sketch of this proof. Also, just to clarify what this theorem is saying, they're saying that, okay, we have this set A that's closed. We've got some sequence of points in A, x1, x2, x3, x4, and eventually this calms down and starts to converge to something. What this is saying is that if this converges to a point, that point must be in the set A. It can't be the case that this sequence converges somewhere but just outside of A. So this is not possible according to this theorem if A is closed. So if A is closed, a sequence of points that are in A cannot converge to a point outside of A. And if it's the case that every convergent sequence of points of A converges to a point inside of A, then A is closed. For that reverse implication, think about our previous theorem that we just saw. We saw that if a sequence of points converges, if a sequence of distinct points of A converges to a point in A, then that point is a limit point. And we also have that previous theorem that a set is closed if and only if it contains all of its limit points. So basically, those are the ideas that this proof needs to pull together. And again, I encourage you to think about that just a little bit on your own and then read over the proof in the book. A corollary to part A of the theorem above is the following. Let X be a limit point of a subset of A, which is a subset of the metric space XD, then every open set containing X contains infinitely many members of A. So the term corollary means that it's a statement that follows fairly quickly from a previous result. In this case, this follows fairly quickly from part A of the previous theorem. And again, I'm going to make it homework to explain why this corollary follows from theorem A. So that's it for this video and this section of the book.